everyone, we are from Group 7. Today we will be presenting a teaching video on topic iron, also known as ferrum, as a solid material and its coordination chemistry. Iron is a transition metal that widely found in earth crust, as well known for its strength, easily adapts, and widely applications in industry. In this presentation, we will focus how iron behaves as a material in terms of structure and properties, and how it's from different coordination compound in chemistry. Throughout this video, we will explaining the type of solid structure the iron form, its physical properties, the basic coordination chemistry including ligand, geometry, naming, isomerism, and finally the real life applications. So let's begin. Material chemistry, also known as solid state chemistry. It is a branch of chemistry that studies the structure, properties, and behavior of the solid material. It is closely related to fields such as solid state physics, metallurgy, ceramic, and electronics. In daily life, it is important because it helps us to understand how materials are selected and used in buildings, transportation, electronic, healthcare, and sustainable technologies based on their properties like strength, durability, and conductivity.
Iron belongs to group 8 transition metals and show typical properties such as variable oxidation states, mainly plus 2 and plus 3, formation of colored compounds, high melting and boiling points, good conductivity, catalytic behavior, and the ability to form coordination complex. Iron or ferrum has atomic number 26 and is one of the earliest metals used by humans. It was widely used during the Iron Age, replacing bronze due to its higher strength and later become important in the development of steel for modern construction and industry. In terms of group trends, iron is moderately reactive and easily oxidized, forming rust, while other group 8 elements like ruthenium and osmium are more corrosion resistant and generally less reactive. Next, iron shows moderate reactivity among transition metals. Compared to group 1 and group 2 elements, transition metals like iron are generally less reactive. Across period 4, the reactivity of metals generally decreased from left to right due to increasing nuclear charge and higher ionization energy, which makes it more difficult for atoms to lose electrons. Iron has the electron configuration argon 3d6 4s2 with partially filled d orbitals and unpaired electrons, which explain its variable chemical behavior. In terms of periodic properties, iron has a moderate atomic size, electronegativity, and ionization energy. These values gradually change across period 4 due to increasing nuclear charge and poor shielding from the electrons. Iron came from different types of compounds, including ionic compounds such as ferrum chloride and ferrum oxide, coordination complex such as hexa-aqua iron, and metallic structures in pure iron and alloys like steel. This versatility is due to its partially filled d orbitals and ability to show variable oxidation states, mainly plus 2 and plus 3.
Now, we move on to the coordination chemistry of iron, which explains how iron forms complex and how it affects its properties and applications. Iron is a metallic solid with a giant crystal lattice structure. Think of an iron like a large hall filled with fixed chairs. The ions are the chairs that stay in place, while electrons are like people moving freely around the hall. This free movement of electrons allows electricity and heat to pass through easily. Because of this structure, iron forms strong metallic bonding, giving it high conductivity, strength, and high melting point. In terms of crystal structure, iron exists in two main forms depending on temperature. At room temperature, iron has a body-centered cubic structure where atoms are arranged in less closely packed form. At higher temperature, it changes to a face-centered cubic FCC structure which is more closely packed and stable. Iron has the electron configuration argon 3d6 and 4s2. It is a d block element with partially filled d orbitals, which allows it to show variable oxidation states such as positive 2 and positive 3, to form Fe2 plus and Fe3 plus ions. These unpaired electrons are also important because they influence the chemical behavior and magnetic properties of ion complex. There are specific rules for naming coordination compounds. Firstly, the cation is named before the anion. Second, ligands are named before the metal ion and arranged in alphabetical order. Numerical prefixes indicate number of ligands and oxidation state is written in Roman numerals. Lastly, an ion complex ends with 8. To make it easy, you can memorize it as LAM, ligand, alphabetical order, and metal is last. Iron forms coordination compounds by bonding with ligands, which are the species that donate lone pairs of electrons. Common ligands include water, ammonia, and chloride ions. Ligands act like donors, giving electron pairs, while iron acts like a central receiver, forming coordinate bonds. This interaction is important because it increases the stability of iron in complex form and allows it to exist in different chemical environments. Now, moving on to coordination chemistry, iron can also form coordination compounds with ligands. Imagine iron sitting in the center of a 3D cage with 6 ligands positioned evenly around it, like points on a geometric shape. This represents the octahedral geometry, which is commonly formed when iron has a coordination number of 6. Now, let's try a question. Which property explains paramagnetism in ion complex? The correct answer is B. Ion coordination complex can show different types of isomerism. Firstly, geometrical isomerism, where ligands are arranged differently in space, such as cis and transforms in octahedral complex. Second, ionization isomerism, where an ion inside the coordination sphere exchanges with the counter ion. For example, a water chloride ion complex and a water-rich ion chloride complex. Third, coordination isomerism, where ligands are exchanged between two metal complexes. Fourth, hydration isomerism, where water inside the coordination sphere is exchanged with water outside the complex. For example, a chloride water ion complex with crystal water and a fully hydrated ion aqua complex. Fifth, linkage isomerism, which occurs through ambidentate ligands like nitride bond through different atoms such as nitrogen or oxygen. Lastly, for hybridization, ion complex with coordination number 6 that involves 6 ligands around the central ion. For example, ion forms an octahedral complex with water ligands. Each ligand, such as water, donates one lone pair of electrons to ion. So 6 water ligands each contribute one pair of electrons, forming 6 coordinate bonds. To accommodate this 6 electron pairs, ion uses its valence electrons and available orbitals to form 6 equivalent sp3d2 hybrid orbitals. These hybrid orbitals allow ion to form a stable octahedral geometry where the 6 ligands are arranged evenly around the central ion. In conclusion, the coordination chemistry of ion greatly influences its properties. Different ligands, geometries, isomerism, and electron configuration all affect its stability and behavior. This is why ion can form a wide variety of compounds with important application in carriers and industry. It's time for another question. Which complex has octahedral geometry? The correct answer is B.
Our last part is the applications and daily life connection of iron. Iron has many important applications in daily life because of its useful material properties. First, iron is a good conductor of heat and electricity because it contains the localized electrons that move freely within the metallic structure. Imagine the localized electron in iron are like a crowd of people moving freely in large stadium. Because they can move easily in all directions, heat and electricity are transferred efficiently through the metal. These make iron suitable for electrical components, machinery, cookware, and heating system. Second, iron has high melting and boiling points because a large amount of energy is needed to break the strong metallic bonds. Therefore, it is used in engine parts and high-temperature industrial equipment such as furnace. Third, iron is hard and strong, especially in alloys such as steel. This is due to strong metallic bonding and its closely packed structure. Because of this strength, iron is widely used in buildings, bridges, vehicles, tools and machinery where durability and structural support are important. Lastly, pure iron can corrode in moist air by forming rust through oxidation. To improve durability, iron is often coated or alloyed, such as in stainless steel and galvanized steel, which are commonly used in kitchenware, medical tools, bridges, and construction metals. These examples shows how the properties of iron directly influence in practical applications in everyday life.
Next, we briefly look at the personal and career relevance of this topic. Iron is very important in many fields such as engineering, manufacturing, healthcare, and also industrial and material-related industries where material selection and properties are very important. Through this topic, we gain a better understanding of transition metals, coordination chemistry, and how the structure of iron affects its properties and application in real life. We also develop useful skills such as critical thinking, teamwork, problem solving, and presentation skills while completing this project. Overall, this topic helps us understand the strong connection between chemistry and real-world application, and it prepares us for future studies and careers in science, engineering, and technology.
Here are a few questions for you to attempt on your own. You can check the answers on the next page.
In conclusion, iron is a very important transition metal with strong magnetic bonding and useful material properties such as high strength, conductivity, and stability. We also learned that iron forms a various coordination complexes due to its electron configuration, variable oxidation states, and its ability to bond with different ligands, resulting in different geometries and behavior. Overall, iron shows how a material structures and bonding are directly linked to its properties and its wide application in daily life and industry. That is all from our group. Thank you for watching our video.